12 students are to take an exam. The exam room is set out in 3 rows of 4 desks, as can be seen in this diagram. And this was an exam question and the diagram was given. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we need to find a number of ways the students can be arranged in the exam hall. So it starts off simple, part A. Then we've got some more information. 2 of the students, Helen and Nikki, are suspected of cheating in the last exam. How many ways can the students be arranged if Helen and Nikki sit so that one is directly behind the other with no gap in between? It says e.g. 5 and 9. Again, the exam question did say that. So, for example, you might have Helen there and Nikki there. But what you wouldn't have is Helen here and Nikki here. Part C, in how many ways can they be arranged if Helen and Nikki must not sit next to each other in the same row? So, just means that something like this cannot happen. Okay, so we'll start simple. Part A, and it might look confusing because you're probably used to sort of linear, like arranging in a line, but if you think about it, total number of possible arrangements, we've got no restrictions at all. Say the first desk, you've got 12 possibilities, so 12 can sit there. The second desk, you've got 11 possibilities. Next desk, 10, and so on. And so you're going to go all the way down to 1. So part A, it's just 12 factorial. And 12 factorial is 4, 7, 9, 0, 0, 1, 600. So quite a lot. That is 479 million different ways you can arrange these students in 12 desks, if there's no restrictions. So now we bring the restrictions in, and it's more complicated. I'm going to do these in 2 ways. I'll just get rid of this first. So part A, we need to find the ways that Helen and Nikki, so part B even, how many ways can the students be arranged if Helen and Nikki sit so that one is directly behind the other with no gap? So we'll start with thinking, well, we're going to place one and then think where we place the other, and then where can we place the rest. So say we put Helen in this column here. So well, we're thinking about the rows really. So say she goes in here. If we put Helen anywhere along this top row, then Nikki's only going to have 1 possibility. But if we put Helen in the middle row, so say we put Helen here, well, Nikki could go here or here, and it could still sort of satisfy the same thing. So what we need to consider separately, if Helen's in row 1, so we'll call this row 1, or row 3, we'll consider that as one scenario, and we'll consider if she sits in the middle row, row 2, as a separate second scenario. So if Helen sits in row 1 or 3, so she's either on the top row or the front row or the back row. So then you've got to think, well, how many possible seats does Helen have? So Helen could be 1, 2, 3, 4 on the front row, or 1, 2, 3, 4 on the back row. So you've got 8 possibilities for Helen. So that's Helen. So once Helen's selected her seat, so say she selects a seat, Nikki actually only has 1 place she can go. So if Helen had picked this seat, Nikki would have to go in this seat, and so on. So once Helen's picked her seat, Nikki only has 1 possibility. Okay, so then you basically just got to seat everybody else. You've got 10 people to arrange around them, and there's 10 factorial ways you can do that. So this is just arranging everybody else, arranging the rest. Okay, so that's if she sits in rows 1 or 3. So then if she sits in row 2, it's slightly different. So if Helen sits in row 2, so if she sits in the middle row, well, Helen's got 4 possibilities. So you've got 4 places Helen can sit, so 4 ways she can do that. And then you have for Nikki, so once Helen's selected a seat, so whatever one of these she picks, Nikki's got 2 choices then. So 2 for Nikki. And then you've just got to arrange the rest, so 10 factorial. This is just arranging the rest. And these time signs, by the way, just come from the fundamental principle of counting. So if you've got different ways, a number of ways that separate things can happen, the number of ways they can all happen together is you multiply them together. So this is arranging the rest. So I need to do 8 times 1 times 10 factorial plus 4 times 2 times 10 factorial. So 8 times 1 times 10 factorial plus 4 times 2 times 10 factorial. And we're adding because it could happen in this way or in the other way. So we need to add. And the answer to that is 580,60800. That's how many ways. Right, there is another way we could have done this. What you could have done is kind of looked, you could have looked, well, how can you place this Helen Nikki block? So because they need to sit one behind the other, you could kind of make an HN block like that. So kind of tie them together. And think, well, how many ways can this block be organized? So you could put this HN block here, or here, or here, or here. So that's 4 places. Plus, you could do it here, or here, or here, or here. So another way, you could say, well, there's, for this Helen and Nikki block, you've got 1, 2, 3, 4, 5, 6, 7, 8 places to put that. Times, well, you need to consider it both ways around. So this could be an HN or it could be an NH. So there's 2 factorial ways of internally arranging H and N. And then you still have to seat the rest. So there's still 10 factorial to arrange everybody else. So that would still give the same answer. Okay, I'm going to do part C on a separate bit of space. So part C, in how many ways can they be arranged if Helen and Nikki must not sit next to each other in the same row? So again, I'm going to do this in 2 ways. We're going to do it by, first of all, we're going to seat Helen, then we're going to seat Nikki, then we're going to seat the rest. And then the second option, well, we're going to consider how many ways that it could happen, as in if they did sit next to each other on the same row, and then we're going to subtract that. In fact, that's actually probably a lot more effective, but if we show both, remember that the more sort of strategies you've got up your sleeve for this sort of thing, the more chance you've got, because they do get very complicated, and they're all slightly different. So what we're going to do, we're going to put Helen somewhere first. So they must not sit next to each other in the same row. So we need to consider the different scenarios. So if Helen sits on one of the rows at the edge, so on the wing. So if she sits in columns 1 or 4, then say I put Helen there, Nikki only has 1 place that she can't go. But if Helen sits in one of these middle columns, so say Helen goes there, well, then that means that Nikki can't sit here or here. So it is different. So we're going to consider it separately. So if Helen sits in column 1 or 4. So what that means is she's either in this, on the end here, or on the end here. So you think, well, Helen's got how many possibilities? Helen could go 1, 2, 3, 4, 5, 6. So you've got 6 for Helen. 6 places Helen can sit. Once Helen's taken her spot, so remember she's not there, you think, where can Nikki sit? Well, she can't sit where Helen, there's 12 seats total. Helen's already sat in one of them, so she definitely can't sit in that. So that would be 11, but she also can't sit here. So that would leave her 10 options, 10 for Nikki. And then you just have to seat everybody else. So there's now 10 seats left, so there's 10 choices for the first one, 9 for the second, 8 for the third, and so on. it's 10 factorial. So that would be if Helen sits in columns 1 or 4. So if she sits in the middle, so if she sits in 2 or 3, it is slightly different. So we'll get rid of that H. So Helen's somewhere around here. So say Helen's over here. That means Helen has still 6 choices. 1, 2, 3, 4, 5, 6. So 6 for Helen. Nikki has, well, she can't sit where Helen is. So remember, there's 12 choices initially. She can't sit there, so that's 11. She can't sit there, so that's 10. And she can't sit there, so there's 9 possible. 1, 2, 3, 4, 5, 6, 7, 8, 9 options for Nikki. So 9, that's Nikki. And then you've just got to see everybody else. 10 seats, 10 people. You can arrange them in 10 factorial ways. So 10 factorial, that's everybody else. Everyone else. So this. Everyone else. So this, it could happen in this way or this way. So we need to add. So the final calculation is going to be 6 times 10 times 10 factorial plus 6 times 9 times 10 factorial. So that leaves us 413, 683, 413, 683, 200 different ways this can happen. Right, so that is one way of working it out. I'll just leave a bit of space, and we could kind of use this not thing. So when I say not, what I'm going to do, I'm going to make this little HN block, H here and an N there, and I'm going to kind of make them a block. And I'm going to think, well, the total number of ways this could happen, and I'm just going to subtract it. So this block could be placed here, or here, or here. So that's 3 places in the top row, 3 places in the middle row, and 3 places in the back row. So you've got, that's total of 1, 2, 3, 4, 5, 6, 7, 8, 9 positions, this HN block, 9 places. HN block placed times, well, then you need to consider HN or NH. So that would be 2 or 2 factorial ways. This is kind of the internal arrangements of the H and N. HN or NH times, well, then you've just got to see everybody else. So 10 factorial ways, everyone else. And then different from part B. So part B, they actually did ask us about this HN block when they were sat behind each other. Here, they're saying this can't happen. So if it's not, it cannot happen, then we need to take away. So we need our initial answer from part A, which was 12 factorial. 12 factorial total ways these things can be arranged, minus 9 times 2 factorial times 10 factorial. And thankfully that still gives an answer of 413,683,200. So there's still that many ways. Now, one thing that you might think is confusing is why when I do it like this, am I considering the internal arrangements of the H and N, but we're not considering that when we're using the other approach. So if I just think about what we were doing before the block, so we were saying, well, if Helen sits columns 1 of 4, so basically Helen's along here somewhere, so that means that Nikki is probably, say, one such combination might be like that, right? Because Nikki's not allowed to sit here, but this would be one combination that would be included in all of these. So you're saying, well, why aren't we reversing it to make that an N and that an H? But if you think about it, if we consider that the second scenario, we were considering Helen being in columns 2 or 3. So this would have been one of the seats where Helen would have been here in column 2 or 3. So this other combination would have been counted in the second method, and that goes for the in the second scenario, and that also goes for the part B, the beginning way that we did part B. They would have been counted in the second scenario.